interesting. We have a lot of thumbs up. Maybe, oh, I don't know how to sum up. Oh, here, no? Like this, like this. Oh, interesting. I have more reactions than I teach in a class. Okay. So today, okay, we have soon we have so far seen that Big Bang nuclear sensors is very good theory. It perfectly matches the observation, the amount of the uh, elements, and also that Big Bang theory can explain cosmic microwave background. However, there are some questions that Big Bang theory cannot explain. There are four of them. Four of the, I don't say problems, but questions that Big Bang theory cannot answer. And then in this chapter, we're going to look at these four problems, four questions. And then these questions point to the need for the inflation theory. Have you guys heard of inflation theory? That at the beginning of the universe, there was a very rapid expansion, more rapid than the current expansion of the universe by dark energy. There was an exponential expansion of the universe at the beginning. When I was student, I heard about this. I heard of this inflation theory, and then these famous professors are talking about, oh, there was exponential expansion of the universe at the beginning, and I thought, okay, is that imagination? There's no evidence why these guys are talking about something like a sci-fi movie. Who knows there was exponential expansion of the universe at the beginning? So when I first heard about inflation theory, I thought it was like science fiction, sci-fi movie. But later I learned inflation from textbook. Now then I realize that there is a logical requirement that we need exponential expansion of the universe, and it's not imagination of these famous professors, but it's actually science. We have a scientific need for this theory. So I hope you have a similar experience today, that we indeed need inflation theory to explain these four problems. Okay, let's get started. Okay, so let's get started with these four problems that Big Bang theory cannot answer, and then inflation theory instead can explain these four theories very, very beautifully. Okay, let's start it. The problem or question number one is this initial density fluctuation. So if the universe is perfectly homogeneous, then there will be no stars or galaxies. It's just uniform temperature, no fluctuation, there's no gravitational collapse. So, but if we observe CMB here, okay, I told you that at milli-Kelvin level, CMB is very homogeneous. However, at micro-Kelvin level, then CMB has this fluctuation, as you see in this picture. There are some high temperature point and low temperature point, high temperature point, low temperature points. These fluctuations are at micro-Kelvin level. So it's very, very small fluctuation. It's less than 0.1%. However, there is a fluctuation. So And then because of this, in these high density regions, there was a gravitational collapse that created galaxies, and then first galaxies, and then stars, and then planets. So these actually initial density fluctuation is a reason why there are stars or galaxies. However, Big Bang theory cannot explain why these fluctuations are created. So that's the question one. Okay. Yeah, sometimes I say that these fluctuations of the CMB here, 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 because of these, the galaxies are created, and then stars are created, and the planets are created, Earth is created, and humans are created. So I sometimes often, tell students, these are your fathers and mothers. Without these, you're not here. Do you agree? Simon, do you agree? Maybe Simon's
Okay,
not here.
please repeat.
Okay. Okay, that's a question one. Next question. So this is question one. This is question two. Next question is a horizon problem. Okay.
Yeah.
How far can a photon go? Let me scroll down. So this is a question. Let's think about how far photon can go. Okay. Okay, here. How far can a photon go? And this distance is going to create a size of causal connection. Okay. Should I start from the conclusion?
I think we talked about that the last lecture also, right?
Yes, yes.
Yeah.
Okay. Let me explain. Let me start from the conclusion. That may be better way. Okay. So about when we talk about horizon problem, I also talked about, okay, these fluctuations of the CMB in this figure is just microkelvin level, right? So at millikelvin level, CM is very, very uniform. It's all 2.7 Kelvin. So if we look at this region, it's 2.7 Kelvin. This region, 2.7 Kelvin. The fluctuations only microkelvin level. And why temperature is so uniform? Okay, you might think, okay, Simon remember that we talk about mixing of the temperature. We talked about that. So you might think this temperature of the universe is mixed. There was okay, I told you enough. There was enough time for the photons to be mixed. However, if we look at the horizon size is actually very small in the early universe. So particle horizon size is much smaller than this scale of the universe. So, and then this particle horizon size is a maximum size that information, including the temperature, can propagate. So outside of this particle horizon, temperature cannot be uniform. However, the temperature of the universe is very, very uniform. So that is the second horizon problem. And then now I show you that the horizon size, particle horizon size at the very beginning of the universe is much smaller than size of the universe. Okay. And to do that, we're going to think about how far can a photon go. Okay, now we are back on the textbook, back to the textbook. And this decides the size of causal connection, including the temperature mix. Let's start with the Friedmann-Robertson-Walker metric with zero curvature, flat universe, and then we only look at the radial direction. So d phi and d theta is 0. And all light rays goes through the shortest distance, so ds equals 0. Okay, this is our typical assumption, right? We often start from there. Okay. Then let's scroll down, and then Friedmann-Robertson-Walker metric becomes like this: RdR equals CdT, because all theta phi terms have disappeared. And a proper distance traveled by a photon is just integration of this, right? This is by definition. So 0 to time t, we integrate CdT on t. Okay, this is actually because this is photon we are talking about. So this value is going to decide the particle horizon, okay, or event horizon. And in a radiation-dominated universe, we look at it many times by now, or several times by now. Scale factor is square root of t in a radiation-dominated universe. So we put this into this equation, okay? Okay. Here's a little bit of about wording. So when we say event horizon, then we are talking about a horizon that is never have causal connection, even at the t equals infinite. And then when we say particle horizon is something to that time of t. Okay. So when you say event horizon, t equal infinite. Particle horizon, t equal until something. Okay. So event horizon, actually, as Simon remembers, event horizon, we already look at it. It's the same calculation. So if omega equals 1, lambda equals 0, this is Einstein-Tochida universe. There's no dark energy, just dark matter. Then we look at this answer is here, that is. And then, so this is event horizon, t equal infinite, or redshift is infinite. Then in terms of particle horizon, this is going to be 2c divided Hubble constant of that particular z. Okay, and then we are talking about particle horizon at the time of CMB, or recombination. Recombination produce CMB, which I'll explain later. But it's around redshift 1000, actually 1090. So we put this number, and then it becomes like something like this number. Okay, and then if we calculate, this is the particle horizon at the time of the CMB, that is 0.4 megaparsec. That is actually very small. Okay. Cone moving distance to redshift 1000 is about 14,000 megaparsec. So that means 14 gigaparsec, right? So angular diameter distance is, you just divide it 1 plus z, which is 1000, then you get 13 megaparsec. So compared to 13 megaparsec, that is the distance to the CMB, redshift 1000. This is a particle horizon at the time of CMB was emitted. And then this ratio, it gives you angular size of 2 degrees. So this 14 megaparsec, 0.46 megaparsec is just 2 degrees. So from here to here, this is 360 degrees, right? So in 360 degrees, the particle horizon where there's a physical or causal connection, it's only 2 degrees. 2 degrees is the maximum the light can travel by redshift 1000. So what does this mean? This means more than 2 degrees apart, there was a no casual contact. Say this is 2 degrees, then here and here, then there's no causal contact. Photons cannot travel from here to here. So there's no way temperature of here is gonna be propagate to here. Then why CMB is so uniform at very large scale? Well, obviously CMB is observationally, we know CMB temperature is the same up to microkelvin level in different directions. So why CMB is uniform outside of particle horizon? This is the horizon problem, second problem. This Big Bang theory cannot explain. So because if the particle horizon size is 2 degrees, then temperature of the CMB should be very different at each 2 degrees because there's no way to mix the temperature. So this is the second horizon problem. Okay, and then the third one is, it should be easy. It's a monopole problem. Almost, okay, I should have shown this figure. Yeah, okay, I already explained this last week, I think. So the third problem is a monopole problem. Almost all ground uniform theories predict that below Curie temperature, magnetic moments of molecules align with those of their neighbors and create magnetic monopole. Theoretically predicted. And then grand unified theories predict about one monopole per horizon size, which we calculate to be 2 degrees at the GUT temperature. Then we have 360 degrees of the sky. So then there should be many magnetic monopoles in this universe, right? 360 divided by 2 is 180. So there should be hundreds of monopoles on the sky. However, observationally, we never found the monopole. Yeah, we never found monopole. So that's the third problem, monopole problem. So monopole is something like, N or S that exists on its own. So, but we never found it. Whenever we see magnets, there's always N and S together, right, in a pair. We never see, oh, this is a magnet with only N or only S. So we never found monopole. This is, they're very different from electricity. Electricity, we have, plus charge and minus charge that can exist on its own, not in a pair. We have electrons that's minus charge, or proton that's plus charge, and they can exist, right? Theoretically, there's no reason there's no magnetic monopole. So, or even more, GUT is predicting the predicting the presence of the monopole. So why there's no magnetic monopole? That again, Big Bang theory cannot explain. Okay, the last one is the flatness problem. So okay, where is it? Okay, flat progress. Right. Here, as we talked about several times in this class, if we try to observe this curvature, omega k, this is almost zero. And then, yeah, this omega curvature is almost precisely zero. Well, this is very convenient for us because our calculations are simpler. We don't need to use hyperbolic sine or hyperbolic cosine to calculate the volume or distance of the universe, which we needed if k omega curvature is not zero. But then every time we observe, omega curvature is very close to zero in this universe. Why is it? Why this universe is flat? There's no explanation in the Big Bang theory. Theoretically, with curvature can be positive or negative. It can be non-zero. But there is no explanation why it is flat. Okay, so these are the 4 problems of that Big Bang theory cannot explain. Okay, shall we go to the next person? Bahare, what are the 4 problems of the Big Bang that I explained? Can you name one of them? One of it? Yes? Go ahead. I cannot hear Bahare. Is Bahare, you have a microphone problem? Okay, maybe you have a microphone problem. Maybe we go to Dora. Dora, can you name one of the 4 problems of the Big Bang theory? Okay, Bahare, you got it right. Flatness problem. Okay, Dora, next one. Can you name one of them? Is Dora here? Maybe Dora is sleeping. Dora, wake up.
Here.
Oh, you're oh, you're not sleeping. Good.
No.
Okay, one of the problems of the CMB. Hint is here.
Wait a minute. The initial density preservation.
Excellent. It's excellent. Good, Dora. Okay. Next person. Who's next? How do I hear? Next is Gutu. Gutu, what's the next problem? Gutu, are you here? Or maybe you have microphone. You don't have microphone? Horizon problem. Okay, that's good. Okay, next is Liu In Xuan.
Hi.
What's the last problem?
Monopole problem.
Excellent. Oh, good. You guys are not sleeping. That's good. Yes, thank you. Liu In Xuan, monopole problem. So these 4 problems So you just mentioned, right? Monopole problem, horizon problem, flatness problem, and initial density perturbation. Inflation theory can explain. That's why we need inflation theory. Okay. This is how beautiful it is. Okay, maybe we should have a break here. And then next, we are going to talk about inflation theory, how inflation theory can solve these problems. Is there any questions in this part? Okay, if not, shall we have a 15 minutes break? Please come back at 3:55. 3:55. Okay.